right. Hi, everyone. My name is Andreas. I work at the Scalable Builds group at Tweag, the OSPO of Modus Create. And there we focus on scalable polyglot build systems like Bazel and Buck2. And today I'll talk about using Buck2 to build Haskell code. So I thought let's do a little stunt and let's build something while I'm talking. So not sure if you can see that. Right, you'll mostly just see numbers whiz by, so that's okay. So I'll be building Amazonka in the background here, which is a Haskell package to connect to the AWS API. All right, so what I'm going to be talking about here is part of a larger collaboration. You already saw, potentially already saw Ian's talk yesterday from Mercury. On the Tweag side, we have the Scalable Builds group with Claudia and myself, and also a GHC team around Torsten Cheng, who is also speaking right after me in short. And from WellType, Matt and Zubin also contributed to parts of this. But I'll be focusing mostly on the build part. So first, let's talk a bit about motivations. Why do we care about scalable build systems? Well, primarily we want our developers to have a fast feedback loop. And these build systems offer features like distributed caching, so you can benefit from build results that were perhaps built by CI and populated into shared cache. If you do workflows like switching your branches back and forth, do undo cycles, you don't have to build from scratch, but you can benefit from previously cached outputs. You can benefit from distributed builds, so you can scale your build into a large cluster. And these build systems are general purpose. They are extensible, so they work well for projects that involve multiple languages, especially if you have dependencies across language boundaries or complex code generation workflows or things like that. And they also have very good support for cross-platform builds, be it cross-compilation or remote execution for a cross-platform. A bit of background on the Scalable Builds group. So we're also the people who developed the Bazel rules to build Haskell code, and we also contributed to Buck2 and helped with the open sourcing of it. So we have a bit of experience in these things. And Ian already described the target code base yesterday. It's a large Haskell code base with around 1 million lines of code, 10K modules in a single package, and complexities like cross-language dependencies and code generation. But to demo this whole thing, as I mentioned, I want to work on the open source Amazonka project, just the library components, but still. And you can find the example code on GitHub right now. And it's an even larger code base with even more modules. But it has a somewhat flatter dependency graph than the target code base has. However, I was quite pleased to see that I was able to migrate this to Buck2 in a fully automated way just with a single script. Though it is a relatively simple Haskell build, to be fair. All right. Let's give a little bit of an overview of Buck2 actually is. So Buck2 is a build system that was developed by Meta and was open sourced last year. It's the version 2 of Meta's previous build system called Buck, and reportedly 2 times faster than Buck. And Buck ultimately was inspired by Google's build system Blaze, or Bazel as the open source version is called. And to give you a bit of an understanding of how these build systems work, as a user, you're mostly interacting with something called targets. This is what it looks like if you want to declare a Haskell library target. So for example, the Amazonka S3 or the Amazonka core libraries would be declared like this. This language is called Starlark. It's essentially Python-esque. Haskell library here is called a rule. And these rules define targets, and the targets can have dependencies through the dependencies attribute here, which defines a target dependency graph. But then, separately from that, we have the actual build actions that actually produce build artifacts. So these rules, like Haskell library, they can issue multiple build actions, like compile this module or link this library. And the way these actions are defined is when you implement a rule in this language called Starlark, you have to be very explicit about what are the inputs to an action, what are the outputs of an action, and then these artifacts are in the end what defines the dependency graph between the build actions. which the build system then uses to decide how to schedule build actions, and for remote builds it will know, okay, these artifacts are things I need to ship to the remote system, these outputs are things that I need to collect. It also uses this for caching, it uses content address caching, so it'll know what inputs to hash, when to invalidate an action, and so on. All right, let's talk about Haskell build specifically. And in the interest of time, I'll focus on one part in particular, which is that, as all of you probably know, to build Haskell code, you have to compile the modules in dependency order. So if we have a module core that imports a module types in our Amazonka project, then we need to compile the types module before we can compile the core module, because we need the interface file to pass on to the next compilation action. So as we want to make Buck2 build Haskell code, the question then becomes, how do we expose this dependency graph to Buck2? So something important to understand about these build systems is that the target graph, the thing that you define as a user with these Haskell library rules and so on, that one is purely static. There's no such thing as build time target generation or anything of that sort. And the motivation behind this is, as your code base becomes really large, you want to make sure that things like querying dependency graphs or things like this remains very fast. So the first way we could potentially do this is we could have a very coarse-grained action where we just say, you know, Buck2 here is one single action, just invoke GHC make on all these modules and build the thing. But as we saw in the beginning, we have like 10,000 modules in a single target or something like this, so that solution doesn't really fly. Because the problem is, if we change one of those modules, we would invalidate the entire action, so we don't really benefit from the fine-grained caching. There's a little asterisk for Buck2, but I won't spend time on that here. And also for remote execution, it's not ideal because we cannot distribute these 10,000 different compile actions onto many different nodes if it's a single action. So what we really want is we want fine-grained actions where each of those compile steps is a single build action to the build system. So that also means we want to use GHC one-shot mode. And we want to get out of this incrementality. So if we change the core module, for example, and we don't have to rebuild the types module, we can distribute them onto remote execution nodes separately and all that. Okay. So fortunately, Buck2 has a great feature there, which is that it does support a dynamic action graph. So the target graph is static, but the action graph is dynamic. And that's a feature it has over Basel, and one of the reasons why we chose it here. And the way this looks is you kind of, in the beginning, define a black box dynamic action where you say, here's the scope of possible inputs you can look at. Here's the scope of possible outputs you can generate. And then there is a special action. We use something like GHC-M. The output of that can be parsed at build time into our build rule. And then in this build rule, we can dynamically, at build time, generate fine-grained build actions for the individual modules based on this output. But those are regular build actions, so they're like caching, distribution on remote execution nodes, all these kinds of things are applicable. So to better support this, we work on an extension to GHC to produce better JSON-formatted metadata output, dependency graph output. Okay, now let's look at package boundaries in Haskell. So module imports can cross package boundaries, right? So the S3 module here can import the Amazonka core module, but it does not import the Amazonka response module. So if we change response, ideally we don't want to recompile types, right? But in order for Buck2 to realize this, and also be able to schedule them independently and so on, we need to expose this to Buck2. So we want dynamic actions sort of across package boundaries. Buck2 didn't really support this when we started out, so we added a new feature to it called dynamic values, which you can kind of think of like futures. And with that, we're able to actually have module granular builds across package boundaries, and that also allows us to say, build system, please build just this one module and all its dependencies, and that will only compile modules on the way. There won't be any linking or anything of the sort. And if we change a module that our module does not depend on and we run the build again, then we don't recompile. The only action that happens here is running GHC-M again, because we changed an input to that, right? So it has to rerun that, but nothing else reruns. And also, eliminating package boundaries is good for scheduling and parallelism and so on, because if we have the package boundary, if you look at the utilization over time, you find these package boundaries bottlenecks because of having to wait for all the modules of one package to finish. And as we eliminate this, compile actions can freely shift to the left in scheduling, which is great for parallelism and utilizing the machines very well. All right, so what current performance do we get out of this? If I take the Amazonka project, only build the library components locally on my 8-core laptop here, Cabal takes about an hour. And on a local build, Buck2 takes about 2 hours. So you can clearly see we still have some work to do. But if I use a 100-node remote execution cluster, Buck2 builds in 15 minutes. So despite the overhead, I'm already getting real benefits from a day-to-day perspective. And this is what the utilization looks like. On the top is Cabal, and the bottom is Buck2. For the local build, you see my machine is pretty much saturated. So I think mostly what we're seeing is the GHC one-shot mode overhead and maybe some overhead in our rules. And on the remote execution side, it's also utilizing the 100 nodes pretty well. I don't exactly know what happened in the middle there. I suspect somebody else used the same cluster. All right. If I look at a small local build, just a few components, then in this particular case, the local Cabal build takes 34 seconds, and Buck2 actually beats it. And I think here the package boundary elimination probably plays a role for that. And the utilization, you can see, is better for Buck2 in the bottom. Note that the Y scale in the top is a bit, it doesn't go up to the same value, so Buck2 has better utilization here. For an incremental build, if I make a change to a module that is not an ABI changing change, then Cabal takes 7 seconds and Buck2 takes just 1 second in this case. So yeah, some good benefits. There are a bunch of other topics I didn't have time to dive into in detail, but I'll very briefly mention them here. So template Haskell, as I suspect you all know, makes things complicated. GHC wants to load objects, GHC wants to load libraries. So if we have template Haskell modules, then we would end up still depending on link actions, and we don't want that because that causes these package boundaries. We enabled one-shot prefer bytecode so that we only need the interface files, even for template Haskell, and you can see that work here. As a side note, if you want to talk to me about GHC loading object files for template Haskell across package boundaries, you can do it. It's a bit of a fun hack. Then another topic, recompilation avoidance. GHC make mode is very smart about avoiding recompiling modules if it doesn't really have to. But Buck2, its caching and deciding whether build actions invalidate is based on content hashes. So any change to an interface file would invalidate an action, right? Which is one of the reasons why also interface and object file determinism is really important here. But we really only want to invalidate an action when the ABI hash changes, right? So fortunately, we were able to apply the same trick that we applied in Bazel already, which is to use a feature called unused inputs. So we tell the build system, I promise you I don't use this interface file, even though we do. And we put the ABI hash into a separate input, and only that ABI hash input will invalidate the action, and the interface file will not. But future work there is we also want to expose the GHC build plan in a more structured way so that we can improve recompilation avoidance as well. And then finally, I mentioned the one-shot mode overhead that we're suffering. That involves things like GHC startup time, loading package DBs, linking libraries, loading interfaces, and repeat it for every module over and over again. So we want to use a compilation server, or as Buck2 calls it, a persistent worker, to amortize this across modules. So in conclusion, with Buck2, we have an extensible and scalable build system. We get cross-package module granular builds, which is good for incremental and parallel builds. We do suffer from one-shot mode overhead, so we need a compilation server. And we're upstreaming a lot of these things, so GHC patches, Buck2 patches. The Buck2 Haskell rules that we're working on are currently still separate, though they're open source, but we do want to upstream them, but we're making big changes to them at the moment, so that's still waiting. Thank you very much. Looks like something failed. I suspect the network might be at fault here. Oh well, too bad. It worked just before when I was sitting in the chair.
Hi. I guess I had a relatively simple question. Do you have any way to generate all these Buck2 like files, I guess, with the targets, etc., from the imports and from a Cabal file, for example?
Yes, yes. So in fact, for Amazonka, I did that. So if you look into the repository, you'll find a file called something like generate, or so it's mentioned in the README. It's a simple like Haskell script that that generates those targets. I cannot see it right now, but it's the one with the HS extension.
Great, thanks.
Hi, so in Cabal you have parallelism, in GHC you have parallelism, and only recently they learned to cooperate. So the benchmark that you showed, was that with cooperation between Cabal and GHC already or not?
Not yet. So JSM wasn't available in the Cabal version I used. So I just used, for the benchmark, I just used different combinations of Cabal parallelism and GHC parallelism and just picked the best one for Cabal. Yeah.
So what is the result of the compilation? Because if you're like, I assume it's not packages that can be put into the GHC package DB because you're crossing package boundaries. So what do you get at the end? Like if this finishes, what is it that you get?
Yeah, so I mean, you do get out a library, like a shared object or an archive or a binary, an executable. We do generate package DBs. So like to generate the package DB, you don't need to wait to compile all the modules and everything, because it's just metadata. We can do that upfront in the very beginning. We still pass package DBs to GHC for the dependency resolution and all that. We just only pass the interface files that the current module we're compiling actually depends on across package boundaries. So we don't have to wait for any of the other interfaces to finish.
But you had that example where you changed something and then recompiled something in a different package that doesn't depend on that module, even though it depends on the package. But that means that at that point you will have something that depends on like that the package that it depends on didn't get made. It was never linked together. You never got any shared objects for that one. So what does this new thing even depend on? Like,
right, yeah. So I mean, the thing is that we kind of tear apart what it means to build a package. So we're only compiling the modules we actually need on the current path to get the artifact that we want right now. Anything else we could build if you request it, but we don't until you do.
So if you build the like in that example, if you not just build the module that doesn't depend, like that depends on some but not all modules of the other package, but if you build the whole package, then the other package would have been rebuilt as well, just so it has something to depend on.
It would have to be built. It would only have to be rebuilt if the change I made actually changed any of the inputs to the particular build actions in a meaningful way. So for example, if I just add a comment to a source file, that won't change anything. Okay. So yeah.
Okay,
so Buck2 comes with a lot of rules for Haskell targets already. Did you reuse any of that, or did you rewrite the whole thing?
We based on top of that. But so the little asterisk in Buck2 I mentioned before, as I'm sure you're aware, is that Buck2 has this thing called incremental actions, where it kind of takes past outputs as a new input to reuse GHC's own recompilation avoidance. But that doesn't work with remote execution, and that also is a little bit of a hermeticity and reproducibility risk. And so we wanted the scaling and all that. And so, yeah, we started with the upstream Haskell rules, and then started changing them. And by now they're changed quite severely, but yeah, we do want to upstream them so long as Meta accepts, of course, but yeah.
One other quick question. So Buck needs to know about all of the existing installed libraries. How did you manage to do that?
Pardon, sorry?
It needs to know about all of the existing installed packages.
Oh, like you mean how do we install our package dependencies, like package packages or things?
Yes. Right.
Yeah, we use Nix. So we use Nix to provide all the upstream dependencies like I don't know, HTTP client or stuff like this. So we just use Nix. And we have a Nix integration in Buck2 that is fine-grained. So it will lazily fetch or ask Nix to materialize the store paths as they are needed.
Okay, thanks.
Is that awesome Seep's work?
Pardon me?
Is that awesome Seep's work?
So we looked at that work. We ended up going for a slightly different path, but yeah.
All right, let's thank the speaker while the next one sets up.